and welcome. I'm Dr. Pauline Fu. In this video, I will present hypothesis test on categorical data. Specifically, I will conduct goodness of fit test. So the objective is to conduct a goodness of fit test for categorical data. First, we discuss the characteristics of a chi-square test, chi-square distribution. Chi-square also use this letter. Okay, chi-square, not x-square, chi-square. It is like this. So as you can see, it is not symmetric. And the shape depends on degree of freedom. If you have different degree of freedom, you may have this shape. Okay. As the number of degree of freedom increase, it becomes more symmetric. So if you have a very large sample size, you may get this distribution more symmetric. And the value of chi-square is always a positive number. So this is the graphical representation of our chi-square distribution with different degree of freedom. As you can see, when you have a degree of freedom 30, degree of freedom 30, it is more like the normal distribution. Okay. The smaller the degree of freedom, the more skewed to the right. Goodness of fit test, it is used to determine whether frequency distribution follow a specific distribution. And we know frequency is a categorical data. So for example, how many students live on campus versus how many students live off campus. So how many students are frequency count. For the goodness of fit test, the very basic concept is the expected counts. Expected counts. Okay. Suppose that there are n independent trials of an experiment with k greater or equal to 3 mutually exclusive possible outcomes. We use P1 represent the probability of observing the first outcome, and the E1 represent the expected count of first outcome, and the P2 represent the probability of observing the second outcome. E2 represent the expected count of the second outcome, and so on. The expected counts for each possible outcome expressed by EI equal to mu I equal to number of trials n times the probability of each trial, Pi. Okay. So you can say, generally speaking, the expected count, it is just the independent trials times the probability. Now let's find our expected counts. A sociologist wishes to determine whether the distribution of number of years caregiving grandparents are responsible for their grandchildren is different today than it was in 2000. According to United States Census Bureau, in 2000, 22.8% of grandparents have been responsible for their grandchildren less than a year. 23.9% of grandparents have been responsible for their grandchildren for 1 to 2 years. 17.6% of grandparents have been responsible for their grandchildren 3 or 4 years, and 35.7% of grandparents have been responsible for their grandchildren for 5 or more years. If the sociologist randomly selects 1,000 caregiving grandparents, compute the expected number within each category, assuming the distribution has not changed from 2000. Okay, so that is the question. The question asks you to compute the expected number, okay, for each category. So how many categories we have? We have less than 1 year. This is one category. We have 1 year to 2 year category. We have 3, 4 years category, and we have 5 or more years. So total we have 4 different categories. The question asks you to count the expected number for each category if you select sample size 1,000. Okay. So let's list the probability for those 4 categories. The probability for less than 1 year, 22.8%, 1 to 2 year, 23.9%. Those numbers are given, see, 22.8%, 23.9% for second category. Third category, 17.6%, and the last one, 35.7%. Okay, so we have the probability of each category. Next, we use the formula E equal to N times P. So the expected value for less than 1 year, sample size 1,000, multiplied by the probability of less than 1 year, that is 22.8%. And we get expected value 228. And for the expected value for 1 to 2 years old, use sample size N times probability between 1 and 2 years old, sample size 1,000, probability between 1 to 2 years old is 23.9%. So you would expect 23.9. Okay, so by the same token, you can calculate the expected value for 3 to 4 years, 176. The expected value for older than 5 years, 357. Okay, so this is how do you calculate expected value? Use sample size times probability. That is the expected value. After we calculated expected value, we need to do a formula. Okay, we use letter O represent observed value, and the letter E represent expected value. Okay. Now we use observed value minus expected value, and then take square, then divided by expected value. We add them all. The sigma means add them all, and this result is a chi-square distribution with a chi minus 1 degree of freedom. And what is chi? Chi is the number of categories. In this example, how many categories we have? We have 4 categories, so chi equal to 4. So less than 1 year, 1 to 2, 3 to 4, 5 or more, so 4 different categories. If you use the chi distribution, there are some conditions. One condition is all expected frequency are greater or equal to 1. Okay, expected frequency greater equal to 1. Number 2, no more than 20% of expected frequencies are less than 5. So remember what is expected value? Expected value equal to sample size times probability. So to test the hypothesis regarding the distribution, we use the following steps. Step 1, determine the null and alternative hypothesis. The null hypothesis H0 said the random variable follow a certain distribution. H1 is opposite of H0. H1 said the random variable does not follow the distribution in the null hypothesis. So H0 said follows. H1 said does not follow. They are opposite to each other. Okay. Step 2, decide level of significance alpha. Alpha usually is 0.05. It could be any number, okay, 0.1, 0.01, or even 0.2, 0.02, 0.04. Okay. Step 3, calculate the expected count for each category. And we already did this in this example, expected count. How do we count the expected counts? For this example, expected number equal to sample size n times probability. That is the expected count. Yes. Again, the requirements for goodness of fit test are satisfied. Make sure the expected counts greater or equal to 1, no more than 20% of the expected counts are less than 5. The requirements, if the requirements in step 3b, okay, step 3b, this is step 3b. If the requirements are not satisfied, one option is to combine one or more of the low frequency categories into a single category so that the condition may be satisfied after you do the combination. And step 3c, we need to calculate test statistic Remember, any test statistic, it is just a formula. In this chi-square test, the formula is observed O minus expected E square divide expected E and then add them together. Sigma means add them together. Once you have test statistic, you need to find critical value. Okay. Remember, what is the critical value? Critical value is the point beside rejection region or critical region. Okay. What is the critical region? Critical region is the level of significance alpha when you have one-tailed test. So for example, this area is alpha. This area is alpha. And this area called critical region. Critical region has another name, rejection region. Okay. And this point corresponding to this alpha is critical value. That's why we use subscript chi-squared and subscript alpha. And if in step 3, after you calculated chi-square test statistic, okay, if this one is in here, suppose the test statistic is here, you reject H0. Okay, reject H0 means the frequency does not follow the stated distribution. If your test statistic is here, you do not reject H0. Do not reject H0 means the frequency follow some distribution. So remember what is H0, what is H1. H1 side, H0 side, the variable follow a certain distribution. H1 side, the variable does not follow certain distribution. Okay. It is either follow or not follow. So that is the critical value approach or classical approach. Next, p-value approach. After you calculated test statistics chi-square, you compare, you get the p-value based on this chi-square. How? Remember, if this is a chi-square test statistic, the area corresponding to test statistic is the p-value. The area is the p-value. Now let's look at an example. This example is the same as the one we did before. Remember, we calculated the expected frequency. The same example. Okay. So I will not repeat, I will just emphasize some important data. Remember, there are 4 categories. Okay. One category is less than 1 year, and that percentage 22.8. And one category is 1 to 2 years, and that category is 23.9. And then you have 3 to 4 years, that category 7.6%. And lastly, you have 5 or more, that is 35.7%. And this data is based on 2000. Okay. And now the sociologist randomly select 1000. And this scientist obtained the following data. Okay. When he selected 1000, he found 250 less than 1 year, 255 between 1 and 2 years, 162 between 3 to 4 years, 331, 5 or more years. This is what the sociologist found. Okay, it is not from historical data. This is what this sociologist did a study. Okay, his finding. And now we want to test the claim that the distribution, which distribution? This distribution, this is the distribution. This distribution is different today, and this is today. Okay, this distribution is today, than it was in 2000. Remember in 2000, we have these 4 categories here. So these are the 2000. In 2000, we have this distribution. Which distribution? We have those percentage. Okay, 1, 2, 3, 4. Okay, so the question asks you to test. The distribution for today is different than the distribution for 2000. That is the question. Okay. So let's follow the steps. Step 1, state the null and alternative hypothesis. Null hypothesis said the distribution for the number of years caregiving grandparents are responsible for their children is the same today as it was in 2000. So the distribution is the same today as it was in 2000. And H1 said the distribution is different today than it was in 2000. As you can see, they're opposite to each other, H0 and H1. Okay. And step 2, specify alpha. And step 3, we need to calculate the expected counts. Remember, we already did expected counts in example 1. Okay, I will show you. So those numbers we already calculated. Based on what formula? Based on sample size n times p. Okay, so I'll show you just to refresh your memory. We already did say those are the expected counts in this example. Okay, so those are the expected counts. And today, this psychologist get those data. Those are the observed counts. Observed counts. So our question is here is, does the observed count has the same distribution with the expected counts? That is the question. Okay. The observed counts. Okay. So now we calculate test statistic. Remember the formula for test statistic. You have a sigma. This sigma means add them all. Sigma. Okay. So in this example, we'll add them all. Oops. So we use observed value. 252 is observed value minus expected value, 228. So if you compare this number, 228 expected value, 252 observed value. Okay, do the subtraction, square it, then over expected value. And you do this for all the numbers. Then you add them together. Sigma means add them together. So for example, how do you get 255 minus 239. You use observed 255 minus expected 239. Okay, oops. And you square it, divide expected. Okay, so you keep on going. Then you found the test statistic is 6.605. Once you have test statistic, you can use a classical approach to find the critical value. So how do we find the critical value? In chi-square test, we usually just use one tail. So the area is the alpha. Okay, you can use the table. Okay, when you look at the table, you need degree of freedom. Degree of freedom is number of category minus 1. In this example, we have 4 categories. Minus 1, you get 3. That is the degree of freedom. And then you need alpha. Alpha is 0.05, is given in step 2. So now you go to the table. So chi-square table. So this is the chi-square table. Okay. In this table, you identify degree of freedom 3, and then you identify alpha 0.05. The intersection part is 7.815. This number is the critical value. Okay, so we get the critical value from the table. This is one way. The other way, you can get the critical value from Excel. So I'll show you here. To get the critical value from Excel, you type in chi-square, CHISQ. Critical value has identified the INV, represent the critical value. And the chi-square test in chapter 11, usually it is right tail test, so .RT, right tail, and the probability 0.05, degree of freedom 3. Okay. So you get 7.815. Okay, this is the formula. Okay. So this is to show you how to get the critical value. Once you have the critical value, so this is the critical value, 7.815. Now, where is your test statistic? 6.605. So label your test statistic is here, 6.605. Obviously, your test statistic is not in the rejection region. So you do not reject H0. Okay. You do not reject H0. So go back to what is your H0. So you do not reject H0. Means the distribution for the number of years caregiving parents are responsible for their grandchildren is the same today as it was in 2000. This statement is true at 0.05 level of significance. H0, H1 always opposite to each other, so this statement is wrong. H1 said the distribution is different today than it was in 2000. Okay, because we do not reject H0. How do we know we do not reject H0? Because test statistic is not in the rejection region. And where is the rejection region? This little right tail, this is the rejection region or critical region. rejection region. So that is the classical approach. Next, let's use the p-value approach. Remember what is the p-value? P-value is the area corresponding to test statistic. Remember we did test statistic 6.605. So this area is p-value. Okay, and how do I find this p-value? Okay, you can use the table. Here I will going to show you the Excel. So in Excel, if you want to find p-value, you do this, equal CHISQ dot p-value usually have identifier DIST dot RT. This is right tail test. X is 6.605. Degree of freedom is 3. Okay. And you get 0.0856. So this is the formula. Okay. All right, so we get the p-value. Once we get the p-value 0.0856, this p-value obviously greater than 0.05. Remember what is 0.05? That is alpha. When p-value greater than alpha, do not reject H0. Do not reject H0. So we reached the same conclusion as we did using critical approach. So the final conclusion we can say, remember when we do not reject H0, we use a double negative to state our conclusion. So insufficient. There is insufficient evidence to conclude that the distribution for the number of years caregiving grandparents are responsible for their grandchildren is different today than it was in 2000 at 0.05 level of significance. So insufficient, different, double negative means the distribution today is the same as the distribution in 2000. So in summary, what I did in this video, I conduct hypothesis test for goodness of fit. That is for categorical data. We use two approaches. One is a classical approach, compare critical value with test statistic. And we also use a p-value approach. And starting from this lecture, we introduce new concept, chi-square distribution. And observed value, expected value. So those are the key terms and terminology. Thank you so much. I look forward to see you in next lecture.